Just terrible.
Yeah, it was one of those things though where I only had 2 hours of sleep, so even if I came, it probably wouldn't have been very helpful.
Well, you can always catch a nap in class. It's kind of, it's
That's what calculus is.
It's nice and cool in the room, right?
No, okay, so the room that calculus was in, I kid you not, it's freezing. It's like a meat locker in there.
Yeah.
And I have no idea what's going on anyway.
So there was a when I was teaching at Mississippi State, there's a lot of old buildings there, right? Because it's a very old university. And, it's also the ag, they also have a big ag school there because it's one of the land grant universities, right? And so, there was a building that was made that was for, teaching, butchery. I know there's some other term for it, but like how to cut the different meats and, from these kind of, and so the way that this building was set up, right, is that they had a place where they stored the carcasses, right, and then they hung them up and they moved them on a conveyor belt type thing to a different room. And this was still a functioning room. But now at this point, it wasn't only taught for, the way things taught there wasn't these food-related classes. So it happened at one point. It wasn't my class, fortunately, but I think it was like a math class or something was being taught in there, and just these cow carcasses moved in the front of the classroom. So I just think it's a power move by the professor, right? Right after the exams are given back or something.
Just dead bodies.
So fortunately we don't have to deal with that here, although I do agree that some of these rooms are exceedingly cold for no reason, but that's okay.
Next semester during OChem, after one of the exams, you should just come in carrying a giant silicone corpse.
I'm
And
okay.
just toss it on the floor.
I don't need to do that. I'll just come in carrying your hopes and dreams and throw that on the floor. Laura gets a thank you.
A silicone corpse would distract us from that pain.
Anyway.
Right,
So if you find the final, if you use the final and then there's a time to find the final.
So,
Then, yeah.
we good?
Yeah.
Okay. Anyway, we've got 6 classes left, right? We've only got about 2 weeks. Today I've got a couple more problems to kind of wrap up the end of the electrochemistry chapter there, and then depending on how fast we get through these problems, we might start today, or we'll definitely start on Wednesday, kind of going through the bits and pieces of the organic chemistry chapter that we need to go through here, right? So we'll take a pretty sharp turn after we finish the electrochemistry because there's not really going to be much math involved with organic chemistry and those kind of things, right? So it'll be a nice break and kind of hopefully a nice lead into, I think, are all of you guys, who's not taking OChem next semester? Okay, so you're done, huh? Is that, yay? So a couple of you guys, I'll see you then for OChem next semester, and then some of you guys are done after this. So in either case, we'll get a little bit of a dose here and either send you off on your way, or we'll see you again, and that'll be a good summary for what's coming up in the fall, because I know you guys are going to remember that from about 5 months from now, or whenever we come back. Why are you guys laughing again? Yeah.
It's a sympathetic response.
I got it. Anyway, so let's see. I think it's also your last lab this week. Is that right?
Yes.
Okay. So and then you guys will be done with that. We will have a quiz on Wednesday. I'll open that up for you guys then on Wednesday there. It'll be off of the electrochemistry chapter there. So shouldn't be any surprises coming out of it, especially if we get through all the practice problems. You guys will kind of see the point, right? And that is something I want to, the point that I want to make, I think, and I know you guys probably recognize this at this stage in your academic careers also, is why in the world do we do practice problems? Well, of course, we need to go through and understand how to use the equations and yada yada and all these kind of things, right? But remember, the practice problems are also there for you guys to kind of see, what's the whole point of this chapter, right? What are the major ideas and concepts? And so one of the things that becomes challenging in all the chemistry courses, I would say, is why are the questions asked? right? Why do we continue to ask questions about the batteries, right? What are the equations that we need to use over and over and over again, right? So it's not just, hey, can I solve this one problem? It's, hey, I've worked 5 of these problems, they all kind of are structured in the same way. What's the what's the underlying idea behind all these, right? And that's to draw out these bullet points if you guys, happen to make, I guess, when I go through and I study things, the first thing I do is kind of like make those summary worksheets. For any of you guys who had me for lecture last semester, right, I had these worksheets for you guys where I kind of bullet pointed the important topics and these kind of things, right?
No?
Yeah.
Last semester?
Mm-hmm. I can see, right? It's up to you if you want to use them or not. Right? But that's just the way that I approach things, right? Because we have a lot of them.
You mean on Canvas, like
Right.
the chapters?
Yeah.
Oh.
Yeah.
Yeah, I didn't use those.
Yeah, that's fine, right? That you don't have to, right? But the point is, when we have these kind of classes like OChem will be, and biochem especially is, right? You're gonna have just mountains and mountains of data, right? You're gonna have to start to organize this and kind of condense it down and boil it down to get to the important parts, right? And one of the methods of doing that is just kind of looking at the practice problems along the way, right? So always kind of keep that in the back of your mind there, right? The same reason why I give you guys quizzes, not that I mean, trust me, it'd be easier if I just could say, okay, your entire grade on this class is just based on the final exam, right? It'd be easier for me because I only have one thing to grade, right? But the whole reason why we do things the way they do is because first you guys would revolt if that's the way it was, right? You'd come with the pitchforks and the torches if we only had one exam in a semester. But it's also to get you guys just kind of familiar with, what is the important topics along the way. So again, I know you guys know this at this point, but especially when you get to these more complex classes like organic and biochem and the other classes that you guys take too, I can only speak from chemistry, right? Find a way to boil down and condense the information to like, hey, this is an important topic, right? And if you're not sure if it's an important topic, guess what you can do?
Ask the professor.
Yeah, come talk to me, right? Or come talk to Laura. She's gone through these classes also, right? Or come, if you don't find me, if you don't find Laura, go talk to Dr. Barbosa or Dr. Toller or Dr. Freeze, right? All of us can point you guys in the right direction with this stuff, okay? Cool, all right. So, I think that's kind of all the, let's say, informational stuff I need to share. I haven't gotten your guys' exams graded yet. I'm almost done with my OChem exams, and then as soon as I'm done with those, then I can start grading your guys' stuff there. And then I will get that stuff back to you guys this week, though, for sure. Right? So you guys will definitely have that stuff back this week. Probably by Friday, just kind of the way things are going. We've got some interviews this week for another biochem faculty member, and then a couple other meetings and things going on. So it's kind of busy. Not to give excuses for things, just letting you guys know that if I'm not in my office or I don't answer emails immediately, I'm kind of tied up a little bit more than usual this week also, right? Okay, I think that's finally enough of me rambling about non-class related stuff.
And the perfectly timed lectures.
So let's get started with prayer, and then we'll work through a couple of these practice problems that come out of the book here. But Lord, we just thank you yet again for the blessing of another day, and just the blessing of another opportunity, Lord, just to serve our purpose, Lord. And Lord, we just pray that we understand what our purpose is. Lord, we pray that you just put this in our hearts and in our minds. Lord, we want to be these good and faithful servants, Lord, and oftentimes we struggle and we get distracted and we just lose our path, Lord. So we just pray that you just realign our hearts, our minds, and our spirits today, Lord, just to follow you and to seek after you, Lord. And it's there that we find our purpose, Lord. So we just pray that you speak clearly to us, just cut through the noise that comes in our lives, Lord, and just help us to find that quiet time, just to hear that whisper of your voice. And you said that if we seek you out, we'll find you, Lord. So we just pray for that time. We just pray for that desire, and we just pray that you speak to us clearly today. And we just ask all this in your name. Amen. All right. Cool. So here we go. Problem for you guys. We've got a voltaic cell there. We have some information, and I'm asking you to figure out something about indium. I-N. So see what you guys come up with. So the standard cell potential for the following reaction, right, is measured at 1.46 volts, and I'm asking you to calculate E naught of the reduction for indium 3+, okay.
This is one of those things that need an appendix for.
Always. Well, actually, not so true. You can take your appendix out and still be okay, so. Thank you. Let's go for that low-hanging fruit this morning. You will need a list of your half cells, your reduction appendix.
I do not have my book this month.
If only you had some device that might be connected to the internet, wherein you could pull up information about reduction half potentials. So, oh, jeez. That stinks. Yeah. Okay, so what 2 bits of information do we need before we start tackling this problem? Well, first, as we talked about, you guys need some information, right, about the reduction half potentials, right? AKA the table that we've used in what, every practice problem so far, right? And remember me talking about these important bullet points coming out of the chapter? So we need that, and then the second thing we need is a formula, right? So E naught, right, of the cell, right, equals E naught of the cathode minus E naught of the anode, right? Well, we're given information about the standard cell potential. So if they write out standard cell potential, what information are they giving you? Or what is that information about? AKA, what value do we plug it in here in our equation? E naught of the cell, got it? Right, so standard cell potential, right? They're just talking about the E naught part there, got it? So don't get tricked, don't get confused or tricked if they don't explicitly say, hey, this is E naught of the cell, this is the standard cell potential, all right? So just the same terminology, or excuse me, different terminology for the same thing there. So we've got information about this, okay, so now we need information about those two. Remember, this is one of these other important bullet points. How do we know what reaction happens at the cathode or the anode, right? So what happens at the cathode?
Gets reduced.
Reduction, right? So reduction happens at the cathode, so oxidation happens at the anode. So what do we need to do then? We need to look at our equation, and we need to figure out what's getting reduced and what's getting oxidized, right? How do we figure out what's getting reduced and what's getting oxidized? Well, indium goes to indium 3+. So indium 1 plus goes to indium 3+. So it is getting oxidized, right? So oxidation happens at the anode, right? And then bromine, elemental bromine, right, goes to bromine 1 minus. So bromine goes from 0 to 1 minus. I guess I should pick a different color than blue here. Let's do orange. Will that show up? That looks pretty good, right? So our reduction happens with the bromine, so the bromine's gonna be at the cathode. Got it? Do we know what E naught for bromine is? Can we look up that information?
Yes.
Sure, right? So you take a look in the textbook, and you look for information about bromine, right? Plus 2E minus goes to 2Br 1 minus, right? And we find that that is plus 1.06 volts, right? So that should just be coming from one of the tables in your textbook there, right? Okay, so let's plug things in. So 1.46, your E naught of the cell, is equal to plus 1.06 volts minus E naught of the anode, right? And there we go. So I think this is math even we can do in our heads at this point in the morning, right? Good? So E naught of the anode there is going to be equal to the E naught of the reduction for indium, right? Because reduction, right, is the the value that we plug in there for the E naught of the anode, right? That's the value that we would pull out of the table is what it is. Right? Good? Nothing too tricky about this, right? What's the only thing to remember? What's happening at the cathode versus the anode, right? And how can we use those values to plug into the appropriate part of the equation? All right? Easy peasy, right? So, oops, not the voladic.
Wait, so that was it? You don't have to flip the sign?
Well, what's the answer come out to be?
The E naught of the.
Because we're subtracting.
So it comes out to be negative 0.4, right?
Okay.
Right, and remember that all the information on that, this is what I was mentioning there, right? The values that we plug into this equation are all the reduction half potential values, right? I'm not saying it's getting reduced in this problem, but the question is asking, hey, what's the reduction half potential, right? And that's the mental gymnastics we have to be careful of in there, right? But that's a very good question, right? So always double check what the question is asking for there. Did everybody catch that?
No?
No, yes, no?
Maybe, I don't know.
Okay, let me go back here for just a second, right? So remember, this is asking for what is the reduction potential for indium, right? So these are the values. When you take a look at the appendix or table 20.1, right? Those are the voltages that are listed there, right? Those are the reduction half potentials. And those are the values that we plug in to our equation here. Got it? I'm not saying indium's getting reduced in this problem, but the question's asking, hey, what's the reduction half potential? Good? Yeah.
So if you do it with like the other version of that same equation, you get like a positive. So would you just know that like reduction means add a negative?
Yeah, you'd have to be, right, you'd have to go and flip it then, right?
Okay.
Yeah.
But in this case, our answer is negative.
Right, because we're already, this equation implies the use of E naught of the reduction, right? Because that's what's happening, or that's the values that we plug into this equation here. Good? Cool. Right. So a voltaic cell is based or constructed, or whatever you want to say here, based on the following reactions. Okay? So now I'm saying we've got two chunks here, right? we've got a cadmium, we've got a solution of cadmium and some cadmium metal, we've got a solution of tin and a chunk of tin, and I'm saying, hey, let's build a battery out of this. What's E naught of the cell going to be? Right? What's E naught of the cell going to be? So see what you guys can figure out for this.
You said we're starting with the chunk of tin?
That's it. What is it?
You said we're starting with the chunk of tin?
Well, we've got a chunk of tin and cadmium and a solution of tin and cadmium, right? So we basically have those four components there. How could we construct something from that, right?
So this is reduced.
It's more positive than that.
Oh, okay. It's not, oh, okay.
So the more positive one gets oxidized.
No, I mean like.
I have no idea.
Well, that's something we need to know, right? That's one of these important parts of reading those tables. So pull up your table real quick. Right?
So the one that's more positive is more likely to reduce.
It's organized alphabetically by element.
Oh, okay. Do you have your notes for your? Yeah, let's take a look at this here. Right? So take a look at this. Up here is fluorine, right? Down here is lithium. So what does this mean? Right? The more positive, right? More positive is easier for reduction, right? The less positive, easier for oxidation, right? So that's where we're talking more positive versus less positive.
Are they getting up? So that means that this is gonna be the oxidizing agent.
Yes.
Okay.
Yeah. Sorry, I gotta run through my statements in my head there. It's not just, it's my brain processor
That's fine.
slowing down.
I was trying to like ask it a different way.
No,
I was
it's
getting it.
it's a good question. It's just, like I said, when I give you guys these like sentences that I remember, I'm not just doing that for show. Like that's literally when I run through and I remember this stuff.
Kind of like how when someone asks you, okay, what letter comes after P, and you gotta say the alphabet song, cause no one knows that off the top of their head.
That's it. Uh-oh. How do we solve something like this? Well, the best way is to do what? Just wait until Dr. H shows you, right? But anyway, so assuming we don't have that option on an exam or something, how do we approach this? I'll give you a hint. You need 2 bits of information. Guess what they might be? You guys tired of me asking the same questions? You guys got the point yet, right? You'll need your reduction table there, right? Your table of half cell reactions, right? And then you'll need the same equation that we've been using over and over and over again. Okay, so first thing is we go and take a look for cadmium and tin, right, in our in those tables somewhere. And if we look this up, let's see here, cadmium was negative 0.40 volts, right? And tin was negative 0.14 volts. Good? Now be careful because some textbooks have a tin 2+ and a tin 4+ redox half reaction there, right? So just make sure you guys are pulling in the right information, okay? Cool, we've got numbers.
Yay!
I'm impressed by them. What do they tell us, though? What is one of these important bullet points that is right in front of Andy right there and is in his notes?
The potential for something to be reduced to the likelihood for it to be.
Okay, the more positive the voltage, the easier it is to be reduced. The easier it is to be reduced, guess what's going to happen to it?
It's gonna be the cathode.
It's going to be reduced at the cathode. Got it, right? So this is all this means. So because we see that tin has the more positive value, right, the bigger number, so to speak, right, the more positive number, we know that it's going to get reduced. And reduction happens at the cathode. Got it? So then we can just plug things into our same equation that we've always been using. There it is, right? So E naught of the cell equals E naught of the cath minus E naught of the anode. Okay? So negative 0.14, right? Minus, and then green, that is negative 0.40. So if we do all that, I get a value of 0.26 volts.
We don't have to flip the minus signs on the anode?
No,
Oh, 'cause it's the reduction of it.
right? These are the reduction half potential values,
Okay.
right? These are the values, this is the same, this was related to what we just got off of the previous problem there, right?
Right.
These are the values from the table that you just plug into here.
Okay.
I'm not saying the anode gets reduced, but in the equation, right, that's where this negative sign comes from, right?
Gotcha.
So if you take a look in the book, there's two equations, and basically the only difference is whether it's a plus or a minus there. I don't care which equation you guys want to use, right? But just make sure that you understand what values go into them, right? You guys with me on this?
Yes.
Let's say we got this wrong and we flip it. Let's say we accidentally confuse our cathode and our anode. What's that number gonna come out to be?
Very different.
Negative 0.26, right? No. Yeah. Right? So what does that mean? What does a negative E naught of the cell tell us? Let me ask you a different question. How many answers have we ever gotten with a negative E naught of the cell?
0,
None so far, right? Why is that?
because it doesn't happen.
It's not that it doesn't happen. Towards the end of the chapter, we related what? We related three important values together. We
And
related E naught, we related what? G, and we related K. Got it? And so there's three important things to remember about this. Or excuse me, there's not three important things. There's important things to remember about those values. Let's see if we can find it real quick. Where was it? It's gotta be before this. Cool. So, what does this tell us? Up at the top there. E naught of the cell greater than 0 means it's
spontaneous.
spontaneous in the direction that it's written. Got it? So if you have a negative value, guess what that tells us?
It's backwards.
It's not spontaneous in that direction, so what's the reaction which way is the reaction gonna go?
The other way.
The opposite direction, right? So this is why if there's a lab that we end up doing some, I don't think you guys are doing it, right? But where you end up making your own batteries and like we get you guys to figure out how to connect the wires. And what you'll see is that sometimes if you read a negative value, right, you just flip the wires, right? And then you have what the voltage that it's supposed to be, right? The reaction's still gonna happen, but it's in the opposite way that you guys have it written. Got it? Does that make sense? So if you're on an exam, you get a negative value for E naught of the cell, first of all, double check your math, right? That's always the first thing. And second of all, if you're 100% sure on your math, then just make sure that make sure to double check what the question is asking too, okay? But it's also important to remember what in the world does a positive or negative E naught of the cell tell us, right? It's whether it's spontaneous or not, okay? In the direction that it's written. Everybody with me on this one? Okay. Is it here? Nope. There it is. Cool. Almost as if I had this planned. Are these reactions spontaneous as they are written? Where's your pencil?
It's a long story.
This is college, Doc, don't ask questions you don't want the answer to.
Don't ask questions I don't want the answer to.
So is it the anode is reduced?
Reduction happens at the cathode. I like big red cats. question, I'll just make the point again. You're gonna need the two same bits of information here, you're gonna need your tables and you're gonna need your equation, right? Then what we need to do is just pull out what's getting reduced and what's oxidized from each one of those problems, right? And once you do that, right, you can figure out what the cathode and the anode are, then you can plug in the values that you guys pull from the table, right? So we're approaching this in exactly the same way that we've been doing all the other ones, correct? So just to kind of make it explicit here, right, for the first problem there, right, copper solid is going to copper 2 plus, right? And hydronium, H plus is going to H2 gas, right? So this is getting oxidized. This is getting reduced. Okay. So that tells us which one's the cathode, the anode, right? Good? Once we know that, we can just fill in our equation, right? So E naught of this cell, right, equals the cathode minus the anode, right? So 0 minus plus 0.34, oops, 34 volts. So E naught of the cell for this first reaction is negative 0.34 volts.
But isn't that number for copper,
Mm-hmm.
That's the reduction.
isn't that the opposite?
What value goes into this equation? The reduction half potentials.
But the number for the reduction is giving us the opposite reaction, where,
That's correct. I'm not saying what reaction is happening here. I'm saying what value goes into that equation,
so it doesn't.
right?
Huh? I thought if you're dealing with the equation being flipped, then doesn't that also flip the value of E?
Right? E naught of the cathode minus E naught of the anode, right? It's the reduction half potential at the cathode, the reduction half potential at the anode. Those are the values that get plugged into the equation.
Even if the equation is written, even if like the chemical equation is written backwards, it's the same number.
Correct. I'm not saying I'm saying the reduction happens at one and the oxidation happens at the other. Okay, so let me ask you guys a question, right? So, you guys pointed out that copper is getting oxidized, correct?
Yes.
From the table, everything was written as a reduction, yes? What value comes out of the table?
Positive.
Negative one?
No.
No, positive one.
0.34.
Yeah.
So what value, right, if I multiply by a negative, then what am I really turning that 3.4 into? The oxidation part of it, got it?
Yeah.
So that's why the negative, your question should be, why is there a negative in this equation? That's the reason why. We're accounting for that, right? Now, there's another equation which we talked about, okay? Let's see if I can find it real quick. Right? So either way you want to, either one of those you want to use is fine, right? But you notice the only real difference is this. Right here, we expect you to flip it on your own. Here, you just plug in what comes out of the table, right? You're going to get to the same value, though, right? Does that help them a little bit? So it doesn't matter to me. Either one of those is fine, right?
I think that's it.
Okay. Yes.
But how can you use those numbers and then use that one with the negative, because that makes the copper one more positive, so wouldn't that mean what you need?
You're flipping the reaction, right? What reaction happens at the anode? The oxidation, which is the opposite of what we see out of the table there, right? The whole assessment of more positive comes from the reduction half potentials, the way they are written in the table there. Otherwise, you're flipping it and then.
The cathode? So wouldn't copper be the cathode then? Because it would be more positive?
Oh, so this is the question, right? So hang on to that thought for just a second. Was it here? Right. So what's this question asking? So are the following reactions as they are written spontaneous? Right? Cause what you're saying is, hey, wait a minute, this one's more positive, that should be the, right, that should be the cathode then, right? So as this is written, is this gonna be a spontaneous reaction? No. So what's really gonna happen? The copper reacting with H2 in the opposite direction there, got it? So, but that's the observation to make with this, right? The opposite direction would be spontaneous, and then we would get the cell potential for that, right? Yep.
I'm just looking at the equation here.
Mhm.
Is there still a negative n number of moles transferred? Number of moles of electrons transferred.
For the delta, for the Nernst equation, right?
Mm-hmm.
Yeah.
So that's a negative n. So if you multiply that by that negative value,
Okay.
positive, therefore saying it would be spontaneous.
So you're saying, is it so you're looking at,
Just that negative sign.
right.
So then negative and a negative is positive.
Mm-hmm.
And then
So you have a negative, let's see, you have, let's see, 2, right? And so this, so here we're looking at that, and you're looking at delta G that comes out of this, so positive delta G, right?
Okay. Oh, I see.
Yeah.
Got it.
Okay. You guys with me on this one? I'm sensing some confusion with it.
It's just a lot going on.
That's true. How do we approach all these problems, right? In the same way. Got it? So see what you guys come up with for the second one. Either way, like they'll both tell you kind of the same thing, right? Depending on how you look at it. For me, it's always easier just to go and calculate E naught, because that gives you one number to assess, right?
This equation I'm using uses all the reduction numbers, so it doesn't factor, we're just looking at this.
Yeah.
Kind of good. Pretty good. Excellent. So you're on the right path. Good. I think I saw everyone get the right value for that one. Everyone got about plus 0.8 volts, right? So it's a positive value for E out of the cell, so that's going to be spontaneous, right? Good?
No?
Alright. Let me see then. Oh, you flipped your cathode anode, right? Yeah. So this is getting reduced, right? So that should be here, right? You flipped your cathode anode.
But, wait,
In the way it's written, this is chlorine, right? Elemental form. So 0 to -1, that's a reduction. Right? Reduction happens at the cathode.
reduction is, okay.
Yeah. Cool. Let's see here, which problem do we want to do? Let's do one of these, since we kind of learned that at the end. All right. So calculate how much aluminum gets produced if we run 10 amps through a solution of aluminum chloride for an hour. And kind of hop towards the end of the chapter, one of the last topics that we talked about. Yeah, I can. Basically, starting. Did you find the answers in the book? No.
Oh.
I just found my one weakness.
you.
Yeah. Don't use that one. It's too helpful. So, we'll just check one out. Okay. So page 887. Yeah, I know it's the same line. I'm just saying those are the equations that you need, right? So. So when we see a problem like this is essentially an exercise of unit conversion, right? So very similar to one of the first topics that we learned in all of general chemistry, right? Our, gosh, what's the name?
Dimensional analysis.
Thank you. The dimensional analysis there, right? Where we're just converting one unit into another, okay? But now it's obviously a little bit more complicated than going from centimeters into meters, okay? Because now we have time and amps, and we need to get it into grams. So there's a number of hoops that we have to jump through along the way, okay? But the key part of this is your Faraday constant. Because your Faraday constant, right, the capital F, right, that relates charge to moles of electrons, okay? And that's going to be the key part. So we're going to have to take our amps and our time, calculate charge, then use Faraday's constant to turn that into moles of electrons. Moles of electrons we can relate into moles of the element, right? And then moles of element we can convert into grams of the element. You guys with me on this? So first thing we got to do is calculate charge. So charge is equal to amps, oops, not times. Charge is equal to amps times seconds, okay? So charge is equal to 10 amps. We have 1.0 hours. Convert that into seconds. I can't spell hours this morning. 600 seconds, right? 6 times 10 to the 4th coulombs. Okay. Good? Oops, I'm out of paper on this, so we'll have to kind of squeeze everything together. So now we're going to go through our string of equations here. So we're going to take our charge times Faraday's constant, right? So for every 1 mole of electrons, we have 96,500, right? Moles of electrons. Now we have to pay attention to aluminum, okay? So we're turning aluminum here into solid aluminum. So now we have to pay attention to how many electrons we need per aluminum atom. Got it? And to do that, we need to know the oxidation state. So we take a look at this, there's aluminum, and it's in a 3+ oxidation state there. So we need to add 3 electrons to it. Got it? If I give you a different salt of aluminum, right, then obviously it would change the number of electrons that we need to transfer. Good? So for every 3 moles of electrons, right, we can make 1 mole of aluminum. Right? And then we go back to our good old reliable periodic table. For every 1 mole aluminum, we have 27.06 grams of aluminum. Charge, moles of electrons into moles of aluminum into grams of aluminum. That's all there is to it. Good? And if I did my math right, and if I think it's the same value that the book got, right? I got about 3.4, 3.3 grams here. Okay. Now there was a problem in our notes that we didn't do when we got to it, right? I think it's the last slide in your guys' notes there. We've got some time, so see what you guys can come up with. Right? See what you guys can come up with. Just making sure everyone got this stuff copied down that they need. Now we're going to be kind of working in reverse. I give you the grams, right, or milligrams. And you guys have gotta back out how much time how much time it takes to do this. See if you guys can figure this one out. Here in Rams, you need to.
Badly.
Yeah. Yeah, this doesn't equal that, right? Yes, it,
No?
not if I'm following correctly.
Yeah.
And that equals this, right? Just, so, go back to that one for a second. Just solve for this first, right? So you have this value, work your way back to get that. Good? Yeah. Careful here. Oh, I see, okay, never mind, ignore me for a second, go ahead. Sorry, I see, okay. Good. Good. Mm-hmm. Yeah. You guys got it. Let me knock this out for you guys here real quick, since we're running a little bit low on time. So first thing, convert this into, grams, right? So 0.325 grams of copper, okay? We're gonna convert that into moles of copper, so 63.55 grams of copper for every 1 mole, okay, of copper. And convert moles of copper into moles of electrons, so for every 1 mole of copper, we have 2 moles of copper 2 plus, okay. And then that moles of electrons can get related to charge. Okay. And if I did all that, I got 987.01 coulombs. And that is equal to, right, amps times time. So for solving for time, I would get 987.01 over 5.6. And I ended up getting about 176 is what it was.
What is it?
176. Good. So there's a couple more problems like this in the book. These are probably some of the trickier ones, just to remember what the conversions are in there. So just work 1 or 2 more of them just to make sure we remember how we can relate moles of electrons to charge and amps and all that kind of stuff. Alrighty, I will see you guys on Wednesday and we'll start the organic chapter. There's not slides for the organic chapter. I'm just gonna be doing this just on, on the board, so to speak, okay? So, we'll be walking through it like that.
Thank you.
We'll see you guys.